So we're going to do some examples within this learning module. We're going to do one kind of end-to-end example, and then I will talk about how that relates to a homework problem. As you start to kind of get your hang of the course, this is like really just our second week of being in full swing. If you really find that these example videos are much more beneficial than just the videos going over the course material, I'm happy to spend my time just making more example videos and kind of let you get the general course material just by reading the book. The reason I'm a little bit hesitant to do that is, as I mentioned beforehand, the book really hasn't been updated a lot since it was written originally, so at least I find it somewhat challenging to read. But the problem is, where I can't talk to you and write on a whiteboard at the same time, like I would if we were in person, I'm not sure how much value me actually just reading through those slides that contain a lot of the figures from the book is providing. So I'm 100% open to feedback. Just email me if you think you would like to see more example videos and less kind of theory videos. So I wanted to do this first example, and let's focus here on the right. I have a bracket with some sort of hook type connection, and I have a pull or a force being applied to it, and I know its magnitude is 100 pounds, and I have some description in this three-dimensional space of its direction. Specifically, I have kind of what you can think of as a measure of azimuth and a measure of elevation. So these aren't directly the two angles that were defined in our prior learning module video. If you remember, in that case, the elevation angle phi was measured kind of as a deflection from the z-axis, and this technically would be denoted as negative because we define theta as a rotation from x to y, but it really emphasizes a key point. You got to work with the information that you're given, and you don't want to rely on just using formulas. You want to be able to visualize the decomposition of a vector as two parts. The first is taking the information that you're given, determining one. You'll always be able to get one of the components of the vector directly, and then the other component of that vector, by converting it into a 2D problem, will allow you to project the vector into a plane containing the other two components of interest. So enough talking, let's actually see how we would do this. So I hope when you see this, you notice that naturally there are two triangles, and the book is kind enough to shade it in this case. In the homework, that won't be the case, but hopefully by that time you'll kind of have the hang of doing it yourself. Even though this lives in 3 dimensions, I can decompose this vector into a triangle consisting of a component which is purely vertical, so that will be aligned along the z-axis, and a component that lives in the xy plane. So the first thing that I'm going to do, big picture, I want x component, y component, and z component. It's a 3-dimension drawing, but I'm only comfortable with working in 2-dimensional space. So I'm going to open up my .cam here just so you can see, and hopefully I will keep it, sorry, it's not obviously smart enough to do a split screen, but I want to keep my original drawing in view. So let's keep it in. And the reason I'm doing this, you do want to be comfortable kind of drawing in 3 dimensions, but I know these videos get long to watch, so I'm trying to keep them as short as possible. So I'm going to just draw this vector at first, this triangle, I should say. And always, you want the hypotenuse of your triangle. So we're always trying to work with right triangles to make the geometry easier. We always want the hypotenuse to correspond to, so this is step 1, as I've called it within the slides, which is basically we're going to find the z component and project into the xy plane. So always choose the hypotenuse of your triangle to be the magnitude that you're given. So if this forged triangle, the hypotenuse represents 100 pounds, we notice that geometrically this side length would correspond to the vertical component, or FC. This angle, which we're given, represents the elevation of this force vector from the xy plane. So this side length actually corresponds to, on my drawing, the component of the force in the xy plane. So it's not purely along the x-axis, or it's not purely along the y-axis. What we'll call it is fxy, to denote that it's the projection of F into the xy plane. So hopefully everyone kind of gets the idea from projections from previous coursework. But if not, do feel free to send me an email. But it's dropping the perpendicular as I've shown in the drawing there. So once I have this triangle, this becomes nearly trivial, right? I can relate, and I will just show this one more time, and then from now on, I won't actually go through writing the ratios. But if I take this angle that I'm given and the hypotenuse that I know, I can find the two components that I'm interested in, FC and FXY. FZ is opposite of 60 degrees. So the sine of 60 degrees by SOHCAHTOA is defined as a ratio of the opposite side length, FC, divided by the hypotenuse, which is 100 pounds, which means that FC is just going to be that 100-pound force magnitude scaled by sine of 60. And I would just say in a similar fashion, FXY, since that projection component is adjacent to 60 degrees, is just going to be 100 times the cos of 60 degrees. Now, the one thing that we should have kind of been a bit careful of is making sure that we're keeping some track of the sign of each of the coordinate axes. So notice that this FZ, according to the geometry that I was given, is aligned in the positive z direction. So I don't, even though this computation that I did would only necessarily give me the magnitude of FZ, I know that it is positive because, as I can see from the drawing, it's in the positive z direction. So let's, in step 2, decompose the projection. And the reason I foreshadowed that a bit is that will come into play when we do this next step. So I have the projection, and I'm going to draw in a coordinate axis system here. Maybe that will help. So in this two-dimensional space, this is the positive x-axis. This is the minus y-axis. So notice that the projection of this vector lives in the positive x-axis and the negative y-axis. Easy for me to say. It's a line. What we have is kind of an angular displacement measured kind of towards the negative y-axis by 45 degrees. So I'm just going to call that fxy. I'm going to drop it perpendicular to the x-axis. So this will be a 90-degree angle. And I was given this measure, which is the angular displacement from positive x to the projection, from positive x to the projection of 45 degrees. And what that means is that I can get fx directly. Notice it is adjacent to the 45-degree angle. So it would just be whatever value the projection fxy was times cos of 45. And this next one is where it gets a little bit tricky. Notice that this side length of the triangle is opposite of the 45-degree angle. So you might be tempted to say, oh, it's just fxy sine 45. But notice that by convention, in order to make your triangle rule work, this is the x component, this is the y component. I have to add in this negative to account for the fact that in my coordinate system, it's moving in not the positive j-hat direction, but the negative j-hat direction. So actually, believe it or not, other than making a computation, I'm done with the problem now, because I know that fx is, well, what is it? Well, it's expressed in terms of the projection fxy, which I know is 100 cos 60. And then I additionally have the factor of cos 45 in there. So just in case you didn't see how that came about, that's fxy. Fy is also involving fxy. Don't forget your negative sign. It's going to be minus 100 cos 60. And going back to the original formula, it's multiplied by the sine of 45. And finally, fc was the easy one that we found at first, 100 sine of 60. So that's my answer here. And I could make a computation. I could round those to 3 sig figs. But once I have it, I know that I can write f as whatever number fx is times I hat plus whatever number fy is times j hat, and then fc times k hat. And we would expect in this case that the y component will be negative. Once we get the signs of this, we want to go back and kind of sanity check, look at this diagram. What should its x component be? Well, it's a positive x component. It's in the negative y direction, but it has a positive z component. So hopefully, as a sanity check, this will come out as plus, this will come out as minus, and this will come out as plus. So I give you a homework problem that is pretty similar to that last example that we did. So here we kind of have some piping type assembly, and we have two angles described. One tells us how this vector in the xy plane is kind of shifted from the positive y-axis towards the positive x-axis. And once we get in that location in the xy plane, we have a measure of how much deflection we have down towards the negative z-axis. So what you want to do is use this 30-degree angle initially in order to determine the z component. Be careful with the sign of the z component, along with the projection of this vector into the xy plane. Once you have the projection of this vector into the xy plane, you can use it to decompose into your x and y components. So hopefully that example was helpful for you. Again, let me know if you would like to see more written examples instead of just talking to slides.